So we have one project ending, one project beginning, and for both the trebuchet and the motor project, you should have sent me your logbooks with all the project in it. And you can link to videos or images in there or whatever, but the entire project should be contained in the logbook, and that is a big part of your grade in this class. And I will get those, like I said, I will get those graded and send you a new grade sheet so you can take a look at how you're doing in the class and ask any questions that you have about that. And we will be going up to, our next stopping point is about a month from now at Thanksgiving break, which begins on Wednesday, 11/25. We don't have any class that day, so we will only meet Monday of that week, of Thanksgiving week. Do you guys have class during Thanksgiving week? None at all? Well, we'll be meeting that Monday, but we won't be doing anything really drastic or anything. We'll mostly just be kind of wrapping up some of the stuff we've done to that point in SketchUp with the 3D drawing, and then we will come back after Thanksgiving and get started on doing some prototyping with the 3D printer. So, nothing to worry about too much. We have this next project involves 3 worksheets, and one of them is this first one is essentially a learning worksheet where you're going to learn about fluid power or hydraulics. We're going to go through that a bit today, and then you will print it off. I will send it to you in an email, and you will print it off and work through this. Give your answers. You actually don't have to print it off if you are in Adobe, the Adobe Reader. You can actually let's see, how can you do this here? This is a new version. Is this the online read? No, this is not. Oh, right here. If you go down on the side of this thing and you can click. No, you can't click edit. You can click fill and sign. So if you click the fill and sign button on the PDF reader, then you can come up here. Somewhere in here, there's a tool where you can put things in like this. So you just click on this, and you can type things into your PDF. Like I can type my name in here, maybe. I can do it on my computer in my office. It's not letting me do it here for some reason. But if your computer lets you do it, you can just type it directly in here, and then you can, depending on what version you have and what computer lets you do, you can save it and send it to me with the things that you've written in, and you don't have to take a picture of it. Otherwise, just do what you've done so far and print it off, fill it in, do the work, fill it in, and take a picture or scan it and send it back. You can also send in the mail. I guess it's just easier, I think, to scan it and email it. So that's kind of what we're going to do today. We're going to go through this sheet, and then we'll do a review of the projects if we have time afterwards. I don't remember how many pages. This is 19 pages, so it'll take a little while. And that will get us through the next project. The next project is all about hydraulics. So let's go ahead and start. Fluid Power Lab, make sure you put your name on it and everything. And you can see here that they've made a little hydraulic arm, and that is the objective. One of the objectives of this next project is to build a fully articulated hydraulic arm. We're going to do it in stages, first by doing some basic hydraulics, and then by building a basic grasping hand, or a scoop or something like that, and then to make a full-on articulated, moving in several different ways kind of arm. So we're going to learn about hydraulic systems, pneumatic systems, cylinders. We're going to learn some science. We're going to learn some engineering, Pascal's law. We're going to learn about liquids and gas. We're going to learn a little bit about pressure. We're going to learn a little bit about energy, friction, viscosity, and work. We're going to have a lot of things we're going to learn about today, but we're not going to go into too much depth with them. So fluid power is where we're going to use a fluid, and often gases are considered fluids. So it's either a gas or a liquid sometime, at some point. And that gas or liquid transmits energy through pressure. And pressure is essentially a type of force that is exerted on a fluid or on a surface or something else. And when you exert a pressure on a fluid, that pressure transmits all the way through the fluid. So you apply the pressure at one end and it exhibits itself at the other end. And that's the advantage here, is that you can transmit the force using pressures in a fluid. There's essentially two types of ways this is done. The first one is pneumatics, and that's where you use a gas to transmit and to store the energy, to put the pressure into it, and usually use air. So you have an air gun, a nail gun here that uses air, and you have an air compressor over here that compresses the air into a high pressure. Then you can use that high pressure to drive the nails in. And then there's hydraulics, where they use a liquid, usually some kind of an oil. And here you can see this big mechanical shovel, thing. Some people call this a backhoe, but it's not really a backhoe. But anyway, it's a big mechanical shovel, and it's both the arm here, all the parts of the arm, its lifting, its extension, and also the bucket movement itself is all hydraulic. In fact, the turning of it is hydraulic as well. This thing has a huge diesel engine on it that is essentially just creating electricity and putting pressure and creating pressure for this hydraulic machine. The electricity is used all over this place, all over the machine, including turning the tracks. That's done with electricity. And then they have electric motors on the tracks. Electric motors also create the pressure in the hydraulic fluid to use for digging. So here they have you list some devices that use pneumatics. Please don't use the devices that are already here. Use something else. And some devices that use hydraulics. So what kind of devices use pneumatic? Can you give me some examples of devices you've seen that use pneumatic pressure? Are you NASCAR fans? Not really NASCAR fans, huh? But have you ever seen a car race where they bring the car into the pit? They bring them into the pit and they take their wheels off. And those wrenches are called impact wrenches. And those are pneumatically driven. So those are driven with air. They can drive them extremely fast. They don't need a lot of power, so you can use pneumatics. And mostly pneumatic things don't need to transmit a lot of energy over a long time. They're usually transmitting a lot of energy in a short time or a little bit of energy over a long time. And so pneumatic devices usually are smaller tools, but there are lots of them out there. So another pneumatic device is the jaws of life. You ever seen the jaws of life? Those are pneumatic devices. There's all kinds of cutters and wrenches and tools and hammers and nailers and staplers, and lots of construction tools are pneumatic. And the advantage of a pneumatic tool is that you can have one big reservoir of air and have tools all over the place on these hoses running off of this one big air reservoir. The disadvantage, of course, is you have to drag an air hose around with you all the time. But they are very useful, very powerful tools. How about hydraulic devices? What kind of devices are you aware of that use hydraulics? There's a lot of them driving around out in the cornfields right now. Yeah, so tractors often are using hydraulics in them. The combines you ever seen the big corn head on the front of a combine and how it lifts up when they go driving on the road, and then they lower it down when it goes in the cornfield? That's lifted and lowered by hydraulics. Lots of things are using hydraulics in the farm industry and in any industry that uses big trucks and trailers and tractors. These big cranes use hydraulics. They all kinds of things are using hydraulics. So lots of hydraulic devices out there. Also, a very simple thing that often uses hydraulics is if you've ever seen one of these little car jacks that just looks like a little bottle, and you stick a little driver in it, and you turn this driver, and the bottle lifts up. That's actually a hydraulic device as well. Your car has hydraulic shock absorbers in it, and so this is actually what the one in your car looks like. Actually, this is a shock absorber from a car, and you have this fluid inside of here, and you have these two ports here that allow you to insert or either increase the pressure or decrease the pressure on either side of this, on either side of the piston. And if you cut this away, this is what it looks like on the inside. You have two chambers, one on each side of the piston, and the piston is sealed on the walls of the chamber, and then it comes out the end of the cylinder. So this is that silver part here up in the right corner is this red part that's sticking out. And the idea here is that if you apply a pressure on either of these fluid ports, that you either push the rod out or you push the rod in, one or the other. And many cars are designed so that you can adjust this. Especially very expensive cars are designed so that you can adjust the shock absorbers on the car. And for example, sports cars are designed to lower themselves to the ground as they go faster and faster, so that you prevent air from going underneath the car. So this is what we call a double action cylinder, where you can push or pull the cylinder. And this is the same kind of cylinder that you'll find on the tractors and the backhoes and other things like this. You apply the pressure on one end, and it will lift up the bucket as it pushes out the cylinder or pulls it in either way. And if you apply the pressure on the other end, it does just the opposite movement. And here they show that the pressurized fluid in pushes the cylinder out. Pressurized fluid in on the other side pushes the piston in. A single acting cylinder only has one port for putting in the pressurized fluid, and so you can only press it one way, and it depends on what you're using it for, whether the port is on one end or the other of the piston. In this case, they put the pressurized fluid on the back end of the piston, so it only can push it out. And so the only thing that they can do is push the piston out with the pressurized fluid, and then release that pressure and assume that something is going to push the piston back in. And that happens in a lot of situations and a lot of machines as well. For example, the machine that you use to lift up a car is a single action cylinder, because the weight of the car will push the piston back in if you release the pressure under the piston. So those car lifts in the car shop, they just use the weight of the car to push the thing back. There's also the same kind of ideas used in a rotational way with the car engine. If you have, for example, automatic transmission in your car. Automatic transmission in your car is kind of an adaptation of pneumatics. Well, not pneumatics, but hydraulics. We're using high-pressure hydraulic fluid to make things spin, make things turn. And so they kind of have something that shows how that kind of works here, where you have a fluid going through the middle and it's turning these gears, but this is actually a gear pump. So this is the opposite of it. This creates the pressure, but you can also use the pressure to turn the wheels, and then you can make your car run. And that's kind of how cars are run today. It's not exactly how it goes, but it's a similar idea. So then, as you go through this worksheet on your own, you're going to get to these questions. You'll use a cylinder as a pump, and the cylinder will be able to push fluid or pull fluid. So in this case, what we're going to do is we're going to apply a force to this piston here. We're going to push fluid out of this cylinder, and then the fluid will go into this cylinder, And well, actually this one is being pulled out and it pulls this piston in, so it's the other way around. But they're going to give you a scenario and you're going to have to figure out all these questions. Make sure you answer those questions. And what we're going to be doing is we're going to be using the syringes that are in your kit as the cylinders for our hydraulic system. And we've given you several types of cylinders, or several types of these syringes, some small ones, some bigger ones, some medium ones, and some of them have different shapes to them. Some of them just have a little flange up here, and some of them have this great big plastic blotchy looking thing on there. And you can use those to your advantage. Some of them will work better in some situations than others. But they want you to label all the parts on this syringe as if it was a hydraulic cylinder, and it can be used that way. So you're going to have to figure out what those are. And here you can see the syringes being used in a situation, a very simple grasping arm kind of situation where you have 3 cylinders down here which are going to be called the master cylinders. They're essentially your control cylinders. And then each one of those is connected to a cylinder up here, which are going to be the cylinders that are going to do the work. So now we get to talk about what pressure is and learn how to use it to our advantage. So pressure is a force, or a push or a pull, divided by an area that push or pull is applied to. So you have this force that's acting down on this 1 inch by 1 inch square, but it's not just acting in the middle like this arrow suggests. It's actually spread out over the entire inch and acting across the entire surface of that square inch. That is 12 pounds over 1 inch, and we call that 12 pounds per square inch, or 12 psi. But if I apply that same amount of force over 4 square inches, or a place that is 2 inches by 2 inches, so it's 4 square inches total, then it's like you're spreading that 12 pounds evenly to each square inch. And you end up with 12 pounds over 4 square inches. That's your force over your area, just like pressure is defined. Instead of 12 pounds over 1 inch, you get 12 over 4, which is 3 pounds per square inch, or 3 psi. So same amount of force, different areas gives you a different pressure. And we actually see this all the time in the real world. Why do they always tell girls to not use high heels or wear high heels in the gymnasium? Well, because if the girl weighs 100 pounds and she's wearing tennis shoes, then that 100 pounds is spread out over the entire surface of the tennis shoe, which is probably, your average tennis shoes, maybe 2 or 3 inches wide by maybe 10 inches long. So that's 30 square inches for one shoe. And when they're walking across the floor and they're on one shoe, that's 100 pounds over 30 square inches. And so that only ends up being 100 divided by 30, which is about 3 psi. So they're only applying 3 pounds per square inch, which is not so bad. However, if you put all of that force, all of that 100 pounds of their weight on a 1 inch square, then it's 100 pounds per square inch. And most high heels are even smaller than 1 inch square. Some of them are as small as a 1/4 square inch, or even less, a 1/16 of a square inch sometimes. So that can be really bad. That ends up being like 1,000 pounds per square inch if you get it down to a 1/16 of a square inch. If it's 1/16 of a square inch, you have 1,000 pounds or more of 1,000 pounds per square inch or more of pressure. So you go from 3 pounds per square inch when you're wearing tennis shoes to 1,000 pounds per square inch when you're wearing heels and you're walking across the floor. Well, that's going to put a dent in the floor because of that increase in pressure. And that's why they say don't wear heels. So that is kind of the idea of what pressure is. What does it mean? Well, this is an experiment that they want you to do. What they want you to do is they want you to put this syringe on your hand where you have the end of the piston here against your hand. That's kind of the fatter end, and it's about 1/2 square inch. And then they want you to have somebody else push on the syringe, or maybe you can push on the syringe, or maybe push down on the table with this so that the pointy end is down on the table, and push down as hard as you can, and you'll notice that you have no discomfort at all. However, if you flip it over so that the pointy part is on your hand and push down as hard as you can, it will leave a mark on your hand. And it might even hurt a little bit because the area is 1.014. That's only 20%, or actually only 2% of the area of the other side. It's extremely small. So the end result is that if you have the same amount of pressure over a small area, you're going to have essentially a lot more force applied to that area. And that is the idea with hydraulics. We want to take something that has the same pressure on both ends but different forces on both ends so that we can apply a small force on one end and get a big force out the other end. When you're dealing with pressure, you have pressure equals force divided by area, but you can rearrange this equation any way you want, and they're using this equation triangle, this formula triangle to figure that out. So essentially if you have pressure equals force over area, you're using this situation where pressure equals force over area, and you use the triangle to figure out what it's going to be. But if you want to know what the force is, then you're going to cross out the force and you'll see that pressure and area are next to each other, so it says pressure times area. If you want to know the area, then you're going to cross out the A and you're going to get force over pressure in this triangle. And of course, if you just want to know the pressure, you cross out the P and it's force over area just like before. And you can use that to help you to remember. Otherwise, you can just solve it as pretty simple algebra. And they want you to solve that equation for, in this case, they're giving us the pressure, and they're also giving us the area, and they want us to calculate the force that comes out. And so we want to use the one where the force is being solved for, which is this first one, pressure times area, and calculate the force. So we already talked about PSI, pounds per square inch. One pound over 1 inch squared is a PSI. But in physics and sometimes in engineering, we use the standard international units, which are meters and newtons. And 1 Pascal is a 1 Newton per square meter. Excuse me. It turns out that 1 Pascal is a much, much smaller pressure than 1 PSI. A Newton is, let me think if I can remember how many newtons are in a pound. I want to say there's maybe 20 newtons per pound or something like that. No, let's see. 5 newtons per pound. 5 times 2. Yeah, it's about 5 newtons per pound. And so if you did 5 newtons here instead of 1 newton, you would have 5 Pascal. But a meter squared is so much bigger than an inch squared. A meter squared is, I don't know, 1,000 times bigger or 500 times bigger or something like that than an inch squared. And so this unit is still, even if you multiply by 5, it's 500 times smaller. So 1 Pascal is a very small amount of pressure, whereas 1 PSI is not that small. So here they're showing a situation where they're going to use a piston in a cylinder to increase the pressure inside of this air, inside of this volume here. And it turns out that this has to do with a law called Pascal's law. If you have a system, a closed system where there is no openings for the air to get out or for the fluid to leave, and you apply a pressure on one end of the system that creates a pressure in that gas at that part of the system, that pressure will travel through the fluid and it will travel throughout the system until it's equal everywhere. So the pressure inside the tube connecting the two systems is the same as the pressure in here and the same as the pressure in here, as long as the fluid is not moving. So it waits till the fluid stops moving, and then everything is spread out and evenly distributed, and the pressure is the same everywhere. Excuse me. This is a really cool experiment to do, and you should do it. You can put a marshmallow inside of one of your syringes here, and plug up the end of the syringe, and then apply pressure to it. Press this thing in and see what happens, and then press it all the way in without your finger on it and hold, and then put your finger on it and pull it out and see what happens to the marshmallow. It's actually kind of cool to see what happens. And it's actually kind of non-intuitive, believe it or not. Let's see. Don't forget to answer all these questions too, 15 and 16. So, calculating the pressure. How are we going to calculate the pressure? Again, we have our triangle here, pressure equals force over area, or force equals pressure times area. Excuse me, in this case we know the force. We're going to put 20 pounds of force on here, and it's going to be, the area is 1.13 inches squared. Of course, the area is going to be the area of the piston end here. So we're measuring the piston end here. The area of this thing down here, where the needle would go on a normal syringe, is much smaller. But you want to measure how wide the inside of the tube is. That would give it to you. And then you would use that for that force in that area to calculate the pressure by dividing force by area. So, if you have, let's take a look at this nail gun right here. I have a nail gun that looks very similar to this. In fact, I have this very nail gun. I own this nail gun right here. And it's using, it says between 60 and 100 psi, so 60 to 100 pounds per square inch. And I don't know exactly what the force is that's being applied to it, but I'm going to guess that it's the force is probably somewhere in the 1,000-pound range that's being exerted on a piston. So if it's 1,000 pounds of force being applied to the piston, how big is the piston? Let's say it's 100, the pressure is 100. Which equation are we going to use? Go back to our equations back here. We know the pressure is 100, and we know the force, right? This one right here is actually wrong. This area right here should be pressure. This is a typo. So this should be force over pressure to calculate the area. So our force is 1,000, our pressure is 100. What do we get for our area? About 10 inches squared, right? About 10 square inches. Does it look like we have a 10 square inch cylinder on this nail gun? Well, why not? What is this thing up here? Here's the hand of the operator. This big gray thing with the black thing on top, that is the cylinder. And the cylinder ends up being about, I would say on mine, the diameter of it is probably 4 inches, so it's about 2 inches diameter. And how do you calculate the area of something? You take pi r squared, so 2 squared is 4, times pi is 3, so it's about 12 square inches. Is that about right? That's about right? So it's about 10 square inches. I said about 10 square inches for my estimate. It comes out to be 12 square inches. That's pretty close. And that is reasonable, right? So this cylinder is being driven by that force, and that's driving the nails in. Why is it that the cylinder doesn't come flying out of this and go driving into the wood? Why doesn't the cylinder come out and drive into the wood? So why would it drive the nail and not the cylinder? If you have the same amount of force, you have the same amount of pressure on the cylinder as you have on the nail. What makes the nail go into the wood? The nail has a super small area, right? So if the force is equal to pressure over area, the pressure is 100 psi, but what's the area of the end of a nail? Really tiny. Yeah, it's really, really tiny. So what's going to happen here is if you have the same pressure and a tiny little area, you're going to have a huge force, it turns out. So it actually requires a smaller force is what it's really going to show. This is actually a better one to show, actually. For the same pressure, so if we have 100 psi of pressure here in a really tiny area here, then the force is going to have to be humongous to keep that pressure the same, right? You have to have a huge force over a tiny little area to make this ratio the same as it was, to give us the same pressure. And so the big area on the cylinder allows us to put, just a small amount of force. It's not really that small, it's a big amount of force, but it's relatively small for what you'd need to drive that cylinder into the wood. But to drive the nail into the wood, you don't need nearly so much because you've got that tiny little point on the nail. And that's the reason you put a point on a nail. That's the reason you put an edge on a knife, is because it creates that ratio where you need less force to drive things into the wood or into whatever you're doing. Or in other words, the same amount of force, the same amount of pressure gives you a huge amount of force. Okay, so here are some more experiments to do. You're going to connect two pistons. There are two syringes. It doesn't really matter which syringes you use as long as you use two that are the same. In this case, they're using the 10 cc syringes. And if you're short on syringes, you need to tell me right away so I can send some out to you. Or if you know somebody nearby who can get you some syringes, make sure they're not used syringes. But you can use those as well. Try not to use any with me alone. But tell me right away if you need them, and I'll send them out to you. You're going to do some experiments with some fluid in the syringes. And in this case, I think they're just using water. Doesn't say necessarily. But just use some water. And I would recommend putting a little bit of maybe vegetable oil on the inside of the syringe and on the plunger, just so that they move and they slide a little bit easier. Vegetable oil will work, mineral oil works, like baby oil. You can even use like WD-40, I guess, would work. But I would recommend that just to give it a little surface, a little slippery surface, and do that before you put the water in, and it'll work a little bit better. You can always just use oil as well. You can use a little bit of oil, and then it's always just a little bit slippery, and that makes things work quite nicely. In that case, I would say mineral oil is probably the best. Nice skin oil. And they have a bunch of things that you're going to do here, and you're going to answer the questions when you do your experiments. Let's see what else they have here. Okay, so here they're going to talk about master and slave cylinder, and they're going to ask you which ones you think are master and the slave. So just think in terms of which cylinder makes the other one do something, right? That's kind of what's involved. When you're in a car and you press on the brakes, you're using hydraulics. The brakes in a car are hydraulic. So there's a cylinder under the pedal, and there's cylinders at the wheels. Which cylinder is the master cylinder, do you think? The one at the pedal or the one at the wheels? I can't hear you. Are you muted? Yeah, so the pedal is the master cylinder, and then the wheels are, of course, the slave cylinders. And then, which cylinders are going to be bigger? And this is the tough one. This one's hard to figure out. Which cylinders would be bigger, the master or the slaves, in a car brakes? And that's what most people would say, but it's actually the other way around. And let me show you why. Let me... So anyway, remember that pressure equals force over area, right? And let's say that the pressure is always going to stay the same, because it does when you're inside of a hydraulic system. The pressure essentially just stays the same. You press on something, it creates a pressure, and that pressure spreads itself throughout the entire system. So let's make a very simple system. One system that has a small radius or a small area, one side of the system, and one side of the system that has a big area. So we're going to put a piston on each side. Here's the piston on the small side, and here's the piston on the big side. So this area over here we're going to call big A, and this one we'll call little a. And the force that is applied, or that is at each end, we'll call this one big F for the big end. We'll call this one little f for the little end. Okay? And let's see how it works in this equation. If the pressure has to stay the same, we'll just leave P right here in the middle as the same. And that has to equal, on one side or the other, this ratio of force over area. And let's pick one of these to be our slave. Let's pick our master. Let's pick the big end to be our master cylinder. We'll apply some big force F over some big area A, and that's going to equal some number P. Let's say it equals 5, just for kicks and giggles. Let's say that it equals 5. And this is a big number over a big number. It's a big force over a big area, right? Well, over here we have a small area. And we need to make the same number 5. So what needs to happen to the force over here? Can it be a big force over here? It's got to be a small force over here, because if it's a small number over a small number, we can still end up with 5. But if we have a big number over a small number, we'll end up with a really big number. Or if we end up with a small number over a big number, we'll end up with a really small number. But we don't want either big or small. We want to keep it the same at 5, right? So this one has to be small over here. Which one do you want to put on? Which one do you want to provide when you're stopping your car? The small force or the big force? You want to provide a small force, because all you have to provide that force with is your foot. However, at the brakes, what kind of force do you want at the brakes? A big force at the brakes, right? And so it's just the opposite. The master cylinder is actually quite small, and it seems counterintuitive, but in the math it makes perfect sense. It's not obvious to us in our experience, because we don't have much experience with this, and so that's what most counterintuitive things do, is they trick your mind, because you don't have much experience doing this every day. We don't go out and play with hydraulics every day, right? So the master cylinder is actually the small one, and you apply your force there at the brakes, and then it distributes the pressure throughout, and when that pressure spreads over a bigger surface, it's applying more force because it's more area. And that more force translates up into this piston and applies that force to the brakes on your car. Does that make this kind of understandable? Okay, good. And once you understand this and you get this pattern in your head, small force over small area equals big force over big area, it's pretty easy to remember, because small was small, big was big, right? Just got to remember it from the outside. Here they're going to do an activity with friction, so you're going to see what happens when the cylinder and the piston heat up, because they've been moving back and forth, and they have some questions about that. Then they talk about viscosity. So what is viscosity? Viscosity is essentially the amount of friction between a fluid and the container it's in. And it's also the amount of friction between the fluid and itself. So it's kind of like internal friction and fluid friction with its environment, but it also has to do with thickness, right? And the thickness and the viscosity are related to each other, are connected to each other, the reason that they have this. So when you try to squeeze ketchup out of a bottle, you're always left over with some ketchup in the bottle, because it's got a high friction with the bottle. And so it sticks to the bottle really easily. But with water, it's very thin, it has a low viscosity, it doesn't stick to the bottle, it doesn't stick to itself, it spreads out easily. When you dump water on the ground, it spreads out until it's pretty much gone. When you dump ketchup on the ground, you can make a big old pile of ketchup on your plate. especially if it's Heinz, right? So and that's because of internal frictions, internal forces within the ketchup and the forces of friction between the ketchup and the table or the ketchup and the bottle or whatever else. And so they're going to have you arrange some things with friction. Now, you would like to have a fluid with friction that is not too high. You don't want a high friction fluid for your hydraulic machine. However, you also don't necessarily want to have water. Why would you not want to have water? Water is cheap, easy to work with, and it has very low viscosity. But why don't we want to use it for our hydraulic fluid? So it's a decent lubricant, but it's not a great lubricant. But what does it do to metals? Because aren't these things normally metal? Water causes problems with most metals, right? Water causes corrosion with most metals. Mostly because it easily carries oxygen, it easily transfers oxygen to the metals, so the metals oxidize. They rust, or aluminum oxidizes and copper oxidizes, and all these metals that we use oxidize. And so it's not a great idea to use water in an environment where oxidation is bad. Oils, however, do the exact opposite. They have a tendency to protect metals from oxidation, and they have lubrication. So the ideal fluid for a hydraulic system is actually a very thin oil that can handle a lot of heat, because you get a lot of heat as you pump it through the system a lot and as it goes through these cycles. Here they show a non-Newtonian fluid, which is a fluid that has a variable viscosity. And this is a great experiment to do. I highly recommend you do it. Have you ever played with cornstarch and water before, in science class or anything? I really want to fill an entire swimming pool with cornstarch. So then you can run across the pool. It'd be kind of dangerous if it was too deep, though, because you could get sucked in and never be able to get out. But I've actually considered doing it with some kiddie pools for an activity here, and have people run across the kiddie pools. Maybe that'll have to be a STEM club activity we do here. But so there are some fluids that have a variable viscosity depending on how much force you apply to it, and cornstarch and water are that way. So here we have some more stuff to do with hydraulics, and then some more experiments to do. And they have a various things they want you to do, and that will be enough for you to do, easily enough for you to do by Friday. And I'll give you some time on Friday to work on it. But you should at least do all the experiments, or bring your stuff with you on Friday so you can finish those experiments. I would recommend taking this stuff home, doing the experiments at home, filling out the information from the experiments and doing some of the work. And then if you still have time, if you still need time to finish it, you can do it on Friday. But I will give you some time in class on Friday to work on them as well. But on Friday I will be talking about the next hydraulics, the first hydraulics experiment. So this is the workbook. Get it done, and then Friday we'll talk about the first real project that we're going to do with hydraulics. All right? I will email this to you right now. Have a great day. We'll see you Friday.